the reasons why people feel inspired by space. It's because we take our humanity with us when we're doing these grand endeavours. I mean, science is a human endeavour. I know that's part of the curriculum that we have to teach in Australia, and rightfully so, because we cannot remove ourselves from our own humanity. We are humans doing science. And so even though it's a system and a tool of inquiry, it's still done by humans. And I just think that's an incredibly humbling thing. Definitely.
All right. I think I'm going to start the official thing. I could botch this up completely, okay?
No, this is great. I always wonder where people get... I don't even know if I sent you anything, Sam.
No.
I always wonder what
LinkedIn.
the internet... Oh, goodness. Okay, here we go.
No, don't worry. It's not. I'm not going to dig up any... Right. When you were 13... no.
Yes.
Okay.
I will.
Fantastic. Yeah. I can tell the story about our Iranian physicist.
Yeah, he's like an investigative journalist. He's done a lot of homework.
Wow. Okay.
Okay, Renae Sayers, welcome to the Range Project and welcome to Scotch.
Thank you so very much.
All right, so you are the Deputy Director of Curtin Space Science and Technology Centre. You're involved heavily with the BINAR space program.
Yeah.
You are a Young Leader Program Manager for the Australian American Leadership Dialogue. You must get bored easily.
Well, I mean, I tell my daughter that boredom is just your imagination calling. And so I think being bored is a good thing in the sense that it can tell you some interesting things. But yeah, I don't intend to sit still for very long indeed.
It sounds like it. So can you, before we get into all the work that you're doing now with the Space Science and Technology Centre, can I just say SSTC?
Sure thing.
Okay. Before we get into that, can you just give us a sense of like where your curiosity for astrophysics came from and sort of the genesis of all of this?
Yeah, I mean, curiosity, right? Like it's so innately human. And when we just have to watch young kids, like our little baby selves, and they are absolute geniuses at curiosity, and that's that unabashed boldness of discovery. I love it so much. I think something happens somewhere along the lines and we become a little bit more shy with our curiosity, a little bit more maybe bashful, sometimes even shameful of like that we may not know the answer and we should not dally with such fascinations. But I think so much good can come from there. So where did it come from me? So we were talking before about how awesome my parents are. And I think just being able to foster that and provide, they always met me where if I reflect back, I think they always met me where my curiosity was going. And so from a really young age, I showed a deep interest, a fascination with the night sky, with the stars, with our sense of our origins. And I guess that's that philosophical place as well. I wasn't necessarily a kid that broke things to work out how they were made and whether I could do that. I wasn't necessarily
kind of engineering type.
No, I wasn't an engineering kind of nerd. I was a why nerd. I was annoying in that question asking and that sort of those ponderings. And I really loved the way different people would come together and have different questions, and I thought always that was fantastic. So I was a why kid that was very annoying in that respect. And my parents saw that, and met me where my curiosity was. And over the Christmases and birthdays, I would start to have this collection of astronomy books and pictures of these incredible worlds of just vast complexity, like the beauty of physics. Literally, we were able to build these incredible telescopes that collected photons from the dawn of our existence and create these pictures and that we could see as data and make sense of. And I just was so just in awe of it. And so yeah, I had a passion for space with respect to that. I used to sit out, I grew up in the Mount Dandenongs over in Victoria in Melbourne. And so we had beautiful skies and would sit out in the foothills and the trees, and there would be this gorgeous little clearing. And I literally would just sit out there and I would talk to the stars. Like I would debrief my day to the sky, which was kind of a cute thing because I always thought wherever I was, I could always have that with me.
And it sounds like you had some time, to a bit of solitude as a kid and time to just let your imagination wander.
Yeah, for sure. I think, and again, like, what is it that we can do to take our curiosity out for a run or for a train? And
so, what were you curious about as a child? You like, what did you come up with any strange theories that you thought about the sky?
I don't know about theories, but I certainly remember that existential kind of crushing sense of insignificance of like waking up in the middle of the night and just being like, what else is out there? And like, we are nothing. And like, going like, yeah, but no, what is on the other side of the Big Bang? And like, if we're a single universe and like if light, like what else is out there that we can't see ever because we'll never ever get information ever from it, but it could be there. And like, what is the shape of our universe and how do so when we look at like a wormhole, like, is that just because you've like doubled like the space over itself, and then how does it twist with that? And like, could you, like, it was just that I just remembered this deep that deep anxiety of like, I was like, is no one else lying awake at night worrying about these things? So that was genuinely the kind of stuff. I actually had a beautiful moment. We let's just fast forward to this year. We had our space program at SciTech for Meet the Scientist a week, one of the weekends, and this young girl, she was 9, and she said to me, and she just looked up at me and like she was like, I have a question for you, and it was effectively that saying. It was like, oh, I'm looking into the eyes of someone that's just like realized their existential, like, oh my God, insignificance. And she asked me this question. She's like, but what is on the other side of the observable universe? And it was just like, I had this dream and I just can't shake it out. And she was just like, and her mum like had ushered her to me and was just like, she has a question for you. I hope you can help. And it was just that moment of, oh, gosh, it's just our beautiful minds as we try and make sense of ourselves and our place in this universe. And, one of the most incredible things that humanity, I think, has developed as a tool of inquiry is science, and our curiosity is just so innate.
So what makes us lose our curiosity? Because you worked at SciTech for a while, so you would have seen kids of various range of age
and adults when we made our adult.
When do we lose it? Why do we lose it? Who loses it?
Oh, Steve, such a deep question. I think naturally as we. Hi, I'm at Scotch College. I just I think school. I think the desire. Oh, can I say this? Like, I think the desire of coming in, of going. We have a mass cohort of individuals that we need to educate and get through a system and measure them somehow. And I think the diversity of humanity and the different types of intelligences and the different ways that people think and learn and connect. We can't create systems that can accustom for all of that, right? So there's got to be some kind of shortcuts that we create to make sense of that. And I think curiosity, because it can be really scary, I think, one of the things in my TED talk I did about curiosity, lol. No, I did. I love curiosity so much that was my, that was one of my things. I was like, I think it's a pathway for empowerment. But don't be afraid of the unknown, because everything we know has come from there, right? And I most likely found that somewhere written as a quote and decided to take that on as a mission and fold that somewhere into the talk. But it genuinely spoke to me of like, we are so afraid of what we don't know and what we can't comprehend. And there's so many different human responses to that. So I think I loved school. I very much love school, and I think it's an incredible thing, and education genuinely changes lives and the course of humanity. But when we try and create it, so we create a system around it, I think that's a very hard thing, because it's like, I can't measure. Like, you're a human on the other side of that, or maybe ChatGPT. I'm not sure how it is for you at the moment as teachers in education. I know universities are having lots of challenges with it, but I think there's something around when we try and systemize something to the point where I need to measure it, and I need to measure it in ways that I understand. I think that can be one way that we learn to conform to a system rather than learning to trust ourselves a little bit as well. And I think there's, all sorts of things of like what makes us wonderful and weird when we're younger. We don't quite understand that that's our superpower. And when we get a bit older and our sense of
So do you have any
self-
suggestions?
Oh, great
'Cause
question.
there's lots of complaining here, but there's no suggestions.
Oh, it's a very, very
I don't think
valid
there's
point.
any complaining. I think that's a beautifully put. I totally agree with you on that systematizing.
Yeah.
You systematize any group of people, at scale, and then try to measure them in some uniform way.
Yeah, and
It is going to lead to some of those students going, I don't want to be measured that way, and I shouldn't be measured that way, and that way of measuring me doesn't work.
Absolutely. It's a
But
great,
so-
it's a great, I mean, that's pretty much it. I mean, we do it in so many other ways as well, in employment as well, like the world, the world is full of systems like that. And so of course, if we can't find places where that can thrive and flourish and actually deliver to the things that we need it to, for example, in a situation of employment or being able to go, yes, we can progress.
So are you doing your
education.
part in where you work? I imagine that's probably a pretty lofty goal for a lot of students to try and head towards. So
Yeah.
do you feel like that's a place for those kind of kids to be inspired?
Oh, for sure. I mean, so I think that inspiration, I mean, it's like those little seeds, curiosity is powerful because it can really instill that sense of intrinsic motivation. And I think something like a surprise, like, wow, that thing happened, or oh my gosh, that's amazing, that kickstarts something internally with respect to, and if the curiosity engine gets going on the inside. And I think if we can meet that curiosity and something that we're trying to do is use the spark of space, the inspiration of space, to hopefully kind of be the fire lighter in the engine room, to really get that going with respect to thinking about those big questions and what are the questions that we want to ask and what are the problems that we need to solve in order to do that, and what does that reflect on us, our endeavors, when we are trying to build things that explore places that have never gone before, and where we're using these tools of inquiry that are honed over centuries still for new problems. And I think if we can, I love science for that inspirational piece, and I think if we can make that a bit more accessible. So I love space for being so accessible with its again, the diversity we spoke earlier about, the reasons why people feel inspired by space. It's because we take our humanity with us when we're doing these grand endeavours. I mean, science is a human endeavour. I know that's part of the curriculum that we have to teach in Australia, and rightfully so, because we cannot remove ourselves from our own humanity. We are humans doing science. And so even though it's a system and a tool of inquiry, it's still done by humans. And I just think that's an incredibly humbling thing, that we don't know what the questions will be. We don't know what the challenges, what kind of problems we need to solve to overcome challenges, but we do know that we need to take our humanity with it. So it's special.
Well, so on that front, and that's all right. So now let's get to what's going on at the Space Centre, like like as far as like distilling down the
Easy
most
questions.
exciting stuff that you're doing at the Space Centre right now, like for our students who are super enthusiastic in this space, and just our school community, all these people that are enthusiasts in space research and all this stuff you're doing, satellite technology. What is the most exciting stuff going on right now? I love a bit of hyperbole and
But you want to know what's happening behind the scenes. We are putting space in the hands of WA. And what does that mean? Well, we have built, we've in-house design, kids that have gone to uni. I mean, all of our team are graduates here from WA, and our students have come from here, and a lot of our students have actually gone through one particular teacher from mechatronics engineering, right? So, it's amazing. We've got lots of different students coming in from lots of different areas now, which is just beautiful.
I think we have one of our Scott students,
Okay.
Ronnie Fellow-Smith, doing mechatronics right now in third or fourth
Amazing.
year. Absolutely
Yes.
going gangbusters at Curtin, loving it,
Absolutely.
I think. So
Great.
sorry,
Do they want to
he'll-
build spacecraft?
He'll be a jet. Oh yeah.
I'm sure.
Aerospace engineering?
Yeah, I'm not sure, but he's one of those students
Yeah,
who was
he's doing great stuff.
fantastic.
With
Amazing.
Awesome.
drones and things. So building his own drones and teaching other people how to make them.
That's awesome. That's really cool. Really cool. I bet you he's got a healthy dose of curiosity about him.
He does.
Yeah, and service, and a really deep
Yeah.
sense of service, which is great.
Absolutely.
So, sorry, but we digress.
No, that's okay. But when you say service, that's like I like to think that making space in service of others, right? So our program, so the Bin Our Space program, it's Noongar for Fireball. Its origins come from the heritage comes from our Desert Fireball Network project. So when the Space Science and Technology Centre was founded, we became a centre in 2018, but we were a collective of planetary researchers that were trying to uncover the origins and evolution of our solar system through chasing fireballs, and to recover those meteorites, those chunks of space rock, because those bits of rock, they're older than the age of our Earth, and they hold those real amazing clues that can help us unravel some of those mysteries. And you have to build really cool technology to do that. And that was where our collaboration with NASA came from, because we were able to solve some cool things, some interesting problems that they hadn't been able to. And so we're the Australian planetary science representative to NASA, mostly courteous of that project and our collective of planetary researchers. So what makes us special is that we want to build spacecraft to explore our solar system. So West Australians can build West Australian technology to serve West Australian science missions that can explore space on the international stage and bring back data from other planets, other moons, asteroids, and of course be able to look back down on our Earth as well and make sense of
why is
some
Western
of the
Australia a
grand
good
challenges.
place for that?
Because we're here. There's a number of reasons. I mean, because I guess the heritage of the Desert Fireball Network is a big part of it.
So can you explain the Fireball Network to people
Yeah,
who don't know what it is?
of
Just
course.
a little summary.
Yeah, of course. So when it's the night, when you're out at night and you look up and you see a fireball in the sky or a shooting star, that's literally a chunk of space rock that's either been knocked off an asteroid or a planet or a moon. And it's been gobbled up in our atmosphere, and it hits our atmosphere and burns really brightly. And those really big ones, they're called fireballs. And we really like those because often they drop meteorites, and meteorites are those rocks. So here's a quick, so if it's a meteoroid, like an asteroid out in space, if it's a meteorite is when it's right there in your hand or on the ground.
They're not cylindrical, are they?
No.
Okay.
No, not so.
Because we were going through some a rock collection the other day, and we were like, sure, had all these cylindrical.
They
things
look
on it.
like. Do they look like core samples? Maybe. Interesting.
Mm,
Or was it a
no,
natural?
Yeah, natural cylinder, maybe thunder eggs or something. I'm not sure. We thought they might have been meteorites.
Yeah. So the way to pick out a meteorite. So and a meteor. So that's the other thing. A meteorite is right in front of you. A meteor. Check it out in the sky. So it's a fun shorthand when you're out camping next time.
Yeah, we'll cut that out later.
I think you're going to cut a lot of this out later. But the shorthand, meteorites, they've got this thing called a fusion crust because they've had to burn up in the atmosphere, and sometimes they've got this sort of like molten kind of like laminar flow style over the rock face because of the melting rock. They also can look like Play-Doh where you've like dimpled it with your fingers as well. It could be pockmarked. But the funny thing is when you're out in the desert looking for these particular space rocks, meteorite or meteorong, often they look like kangaroo poo. And so you'd carry a big stick and it's literally
So
like
with your Fireball
pigs.
observatory,
Right.
you can actually be accurate enough to know where they land.
Yeah, and that's the special thing. So yes, kangaroo poo aside, we
To what kind of accuracy?
yeah. So to answer that question, I'll go back a few steps. So the answer to that is within about 200 meters. The rocks we have found and recovered have been within about 200 meters of their predicted fall line or their strewn field. How we get to that, which is remarkable when you think this thing has just literally been going around for 4.6 billion years, and then we watch it enter and then we're like, oh, there it goes. is that we've been able to link what we see with this fireball. So we developed these camera techniques, these observatories that are dotted out in the desert, and they're watching the sky all night, every night. It's effectively a DLSR camera with some very amazing kind of like in-house technology solutions to make it do some very unique things. And so we take these long exposure images, and if we see a fireball, it means that, and it's seen by other observatories around, we can do something like we can triangulate its orbit, which means that we can see it from different angles, which means we can basically wind the clock back and work out where that bit of rock came from in the solar system, which is really, really important.
So is this from like lab techs plotting the points, or are you using AI for this?
So it's server side. So it's happening in sort of like near real time server side. So you're doing the data pipeline reduction, basically like server side. So by where the cameras are, and then you're able to then pop that out with like the data reduction pipeline. There's some very cool things that happen with that. We've got some amazing scientists. It's headed up by Dr. Ali Sansom, and her part of this was looking at how you can model the mass as it changes through bright flight, and then how to predict what it is in dark flight, and therefore where it will land. So when we see something burning, we can use observations, but then when it stops burning, it goes into something called dark flight, and that's where we click over to predictions. And so if we can work out its orbit, where it came from in the solar system, and then we can kind of wind the clock forward with predictions.
You can only see it when it's burning.
Yeah.
And you don't really know how big it is.
Well, so that's how you...
Bigger things would act quite differently falling through the atmosphere, yeah?
Absolutely. And
so you have to be able to predict the mass.
Because mass will help you work out the modelling of where that strewn field or that fall line is. And so you create this amazing prediction of if the mass, like if given the wind conditions and the differing masses, that will give you your kind of...
and so how accurate have you been on the mass on the ground? So we've talked about how accurate you were in terms of...
Great question.
Like how close you are to it, but how accurate are you to the dimensions?
Yeah, it's a kind of a near enough is good enough situation, because it helps us work out what kind of rock, like, because you see lots of different rocks out there. So you actually can recover meteorites that weren't the ones that you saw fall as well. So what that helps us do is work out, is this a rock that can fit in our hand, or is this the size of a chair, which would definitely not happen, because obviously that would be a very big explosion in the sky, not explosion, a very, very high energy fireball. But is this like a pebble, or is this like something that you could hold in your hand, like a baseball size, or like the size of a brick, etc. So that will help us narrow down where we think it might be. And so when you see it, you can like, ta-da, yes, we'd expect it to be a bit of a mass of this size. It's a great question, because it also we don't know what it's made of as well.
Yeah.
So that can, like, meteorites are often quite heavy for their size, often because they might have a high iron content, for example. But I am veering into definitely not my expertise with respect to that. I'd have to look that up, and I'd have to ask our team.
Interested.
So,
but
no, you finish.
I was just going to close this one off, because the thing that I love about this is that why do we need to do this, right? So we can collect those rocks. Yes, they can help us uncover the origins, evolution of our solar system. The problem is that we have so many of these beautiful samples of meteorites. There's like over 60,000 known to science. A lot of them we recover in Antarctica, because it's a great place to find dark rocks, by the way. So what's so special about what we do? Well, remember how I was saying we know where the pre-Earth orbits are. We can derive that. So we've got one of the largest data banks in history of observed meteorites, or I should say observed fireballs in their pre-Earth orbit. So we've built up a geological kind of context map of the solar system of these small bodies. The thing is, only 30 or 40 meteorites have those known orbits. out of the 60-odd thousand of them. So we're literally trying to piece together the puzzle of our origins with one hand tied behind our back. It's like if we got a bunch of rocks from Australia, all around Australia, and we tipped them out on this table right now, and I'm like, tell me the history of of this land, you would first have to ask, well, where did they come from? And we don't know where these rocks come from. And so that was the power of the Desert Fireball Network, to be able to
track them,
to connect their pre-Earth orbit, and then be able to predict where they are, whether they dropped, whether they were droppers, so of a significant size. And also then, because we chose very deliberately where to set this up, i.e. the desert, particularly the Nullarbor, it's one of the best places. In fact, other than the Antarctic, as we said, the Antarctic surveys they do, it's actually one of the best places to search for meteorites. So the chance of finding and recovering them.
Clear skies and
it's
less light
remoteness
pollution.
and
Oh no, this is literally going to recover them.
Oh,
like you
okay.
literally can just walk for 10 kilometers in a straight line and like find your rock. And the cool thing, speaking about drones, is that now our project has got to a place where we've got this cool PhD student called Seamus, and he developed this machine learning algorithm that will help us and has recovered a meteorite. This is so cool. I can't believe I'm only talking about it right now. To help searching for these meteorites, because that's the really hard bit, the human part, going out and searching for these rocks. And so if we want to nerd out a little bit.
This gets even more accurate then, is to where you could just walk straight out and go, it's exactly there. Yeah.
Well, the whole point is that the drone is taking all these images, right? And so if you have an intelligent system that's able to make sense of what it's looking at, then it can help you narrow down where you should be looking for the rock, right? But then you have to train the system. You have to train the system to know what is a rock, what is not, what is a meteorite rock, what is a not meteorite, a meteorong. And there's a whole other podcast that we could nerd out with him on how he did that, because it's a very biased data set, a training data set, because we only have a handful of examples of meteorites. So,
and you probably didn't take aerial footage of when you... Did they have tracks where they land or anything like that, or is it just a big...
Oh, I mean, it's just like if I dropped my phone off the side of the table, like it's it's not necessarily a big hole punching scenario. Although one of the first ones we recovered with the new the digital fireball network, Murili, was out in a salt lake in South Australia, and it did kind of get, it was like there was a little mini crater, right? Because it was buried in that sort of muddy salt. And Phil, there's some great footage of him like digging this thing out, and he had it in his hand, and there was like rains coming over, and they had dirt bikes in the middle of this salt lake, and it was like, we have to go. And there was people around in this light aircraft like going around, because it was like, we saw where it could be. And
you would have been right at home there, Steve.
Yeah.
Adventure. Sorry, we're spending a lot of time on the Desert Fireball Network, and rightly so, because it's amazing. But I tell you what, we should get. You should bring. I'll bring some of our SSTC Desert Fireball Network friends back in, and
that would be amazing. That would be amazing.
How we do stuff with NASA. That's where a lot of our partnership for planetary science came from.
So to sort of segue from that to the BINAR space program, which is massive. Right, and one of the centerpieces, I guess, of the whole of the Space Centre and the work you're doing. Did you say there was some sort of spin-off technologies that went into BINAR that you discovered through that Fireball Observatory, or not really? That's just a totally separate...
No. That's absolutely the heritage of our Desert Fireball Network. So our ability to do really cool things with our sort of microelectronics and building,
hacking and tinkering.
Yeah. So basically hacking the what we call COTS, the off-the-shelf consumer technology or hardware, and being able to overlay our own stuff over the top and make it do the things that we needed to do. At the heart of BINAR, really, it began as a couple of projects of investigating some of these spacecraft subsystems. And then they iterated into, well, what if we integrated them all together like we did with the DFN, like we did with our printed circuit boards. And so they started... After we had tried to buy stuff off the shelf. Usually how it works is when, particularly for research and even schools, CubeSats, particularly 1U. So if you think of a tissue box, like a square tissue box, that's the size of a 1U. 10 by 10 by 10 centimeters. And they're a really great platform to try stuff out and to learn. And so they're the fodder of universities, if you will, university or research projects or school projects to launch things, either off the International Space Station or in other ways that you launch and deploy on orbit. And so we began that process. We're like, let's buy some stuff. And we found that we could probably, because of the Desert Fireball Network, we could probably do a better job by just like putting it all together, right? When you think about how much wasted space there is by buying lots of things separately and trying to sandwich them together rather than just designing it. We were working out that a lot of the errors come from when you have to hand assemble things. So why don't they like integrate it digitally, and so you can design it in CAD and then send it away to be printed like consumer hardware and advanced manufacturing techniques. And so it's a lot cheaper, and you can kind of design it, send it away, get it printed and picked, and then come back and start testing on it. And so the concept that really was the birth of Binar was, why don't we put an entire spacecraft on a single circuit board? And what that ended up doing was not only being our own in-house design, and therefore, we could continue iterating. We knew how it all worked. We knew how to break it, and we knew how to iterate. It also meant that a 1U suddenly became a lot more useful because there was so much more space. So you could put some instruments, you could put some more cameras, you could put these sensors, and suddenly our 1U became a thing that we could do useful things on. Normally, CubeSats, if you want a bigger lens or a bigger device or like instrument, you have to have something bigger like 3U or 6U, for example, because the guts of the spacecraft, the bus, takes up so much room, and you don't have as much space left for your mission.
I'm jumping ahead here, but once I've just thought about this. So you got these little, essentially satellites, things that you're shooting up into space. How long do they survive up there for?
Yeah, and so this is where we go back to Binar, right? The Noongar for Fireball. Because of the Desert Fireball Network heritage, but also it's becoming a fireball. That's the whole thing. Binar burned up like a binner of its namesake. And that's another thing that's really cool about this is when you send them into low Earth orbit, where the ISS is, about 400 kilometers up. We actually, I have the stats right here because it was late last year that we had it orbiting, like it was deteriorating. Oh, here, let me get it for you. And so we actually had the last confirmed orbit was on the 1st of October in 2022. And it completed 5,636 orbits of the Earth over 360 days in space. So that was a pretty good high score for our first attempt.
That's amazing.
Which is pretty fantastic. So it was 150 kilometers up when we got its last kind of recorded orbit. So
did you have any sense of roughly how long it was going to be up there for? Is that a bit of a mystery, or were you like, we think it's...
Yeah, so it can be depending on the space weather, right? So low Earth orbit, it's still kind of bumping around with our upper atmosphere at that point. And so depending on space weather events and other types of things, as it's interacting with very, very thin atmosphere, it does start to degrade that orbit. It's certainly degraded a lot more quicker than we had originally thought. But again, this was the first time we did it, so we weren't exactly sure.
Is it transmitting information back to you, or how are you getting information from it?
Yeah, so we can pick it up on radars, and when we were talking with our spacecraft, so when you use your ground station and you do an uplink and downlink, so we could get data coming back down from the spacecraft, and it was just a super simple little signal, hello world, we're adorable. Not that it said we're adorable, we were adorable by saying hello world. It was just it was a beacon. Yeah, it was a beacon. And so there's some of the ways in which that you can record those orbits, so we can have that data. But in fact, on our next 3 spacecraft, BINA 2, 3, and 4, one of our PhD students, in fact, one of the original students that worked on BINA, has got a orbit re-entry tracking PhD project, and using iridium comms to track it in as it goes down and down and down as it degrades. And so this is going to be a really interesting project, because we do want to understand what happens to these spacecraft as they re-enter, and particularly with the role of these really novel small spacecraft platforms. Imagine if it wasn't just a 1U, but maybe a 6U or a 12U, and imagine if it had collected something quite interesting and we wanted to have it re-enter, then we need to be able to track it and do some really novel stuff. So it's really cool that one of the PhD projects has that way that we might be able to track it a bit better as it enters, when it re-enters.
Can I just ask you this? What are the rules of putting a satellite up into space? Because we have spoken before a little bit about the challenges of the bureaucratic challenges of getting something up there, and you've got all these, because this is my second question too that I really want to ask you. You've got all these satellites going up into space now with someone like Elon Musk, very polarizing figure, but he's about to just send thousands more satellites up there, and they're all over the place. What's going to happen there? Are we going to get this incredible sort of sea of satellites up there all doing various things? Is there some kind of limit to how many we can have in space and all that kind of stuff?
Yeah, so it's space is an ever congested, contested space, so to speak. And when you talk about Starlink, it's amazing that we've got connectivity around the globe now, but astronomers hate it, obviously, because it affects the ability for us to collect data from distant stars in our cosmic neighborhood, right? So there's some interesting trade-offs that are happening. Space junk. Do you know the movie Gravity, where spoiler alert, but George Clooney and Sandra Bullock, and they're they're in low Earth
I do
orbit.
remember that.
And there was an event that happened, and basically, that's a thing that's modelled. We know that that's a real risk. They definitely do evasive manoeuvres of the International Space Station and of other space assets when it's predicted that there'll be a collision in space. If you think of a shard of paint traveling at the speed of bullet, it can completely wipe out an entire solar panel, which then means that your space asset now no longer can collect the same power, which basically means it's a bit of space junk. And so space junk's a really interesting problem that we're trying to solve. We're trying to understand space traffic management. We're trying to understand basically how we can once those objects are up there, they're up there, right? So with low Earth orbit, it's really interesting. Like spacecraft like BINA, they do burn up because their orbits will degrade and will burn up in the atmosphere. And that's one thing that the Australian Space Agency really wanted to be a sustainable player in space. And so there are high standards that they want to set with respect to, what's your de-orbiting plan and how are you not going to contribute to this space junk problem. So if you have one big asset that then breaks up into lots of smaller assets, then you've basically got a multi-body problem again. So it's a really challenging thing that we'll have to face, and these graveyard orbits exist in different altitudes, and so it'll be really interesting as we launch more and more things. SpaceX, I know, they're the largest. There was the largest launch, the highest amount of space assets in a single launch, and it's just remarkable.
So
it's a real
are they
problem.
putting any regulations? I guess you don't have to go in the same direction of the orbit. I mean, there's things that you could potentially do to minimise impact, or if they break apart, so they all disintegrate upon re-entry or something like. Is anyone giving out these kind of regulations?
Yeah, so things like if your end of mission life, do you take your spacecraft out to a redundant, orbital profile? So it's, not taking up space, if you will, or do you deorbit it and so it gets burnt up upon re-entry? Or does it, again, if it just breaks up there, then it's just there. So you do have to, through your submission, you have to describe how you're being sustainable for that as well. And there's lots of regulations. Space law is fascinating. So if there's anyone out there who's really interested in how we create these like regulations and frameworks and legal precedents in a place like space, and you're interested in that, this is a really cool area. We actually have one of our staff who's finishing up their law degree, and because of their experience with our program, is getting firsthand experience in the difficulties and the challenges and the opportunities in this space. And so we really value that, because as we said, it's not just building the spacecraft, and in some ways building the spacecraft is the easy bit. There's a lot of other things that we have to understand to.
I was going to segue from that, like this idea of having, space lawyers, I guess you could call them.
They are space law for sure.
That'd be a pretty cool thing to put on your CV, wouldn't it?
Well, it's building new careers. This is the whole thing, by exploring and making sense of a lot of this international activity. And absolutely, this is a career now. You can create careers. On that point, actually, I'm thinking about our students here who are graduating, and are real STEM enthusiasts. What other kind of jobs out there are there that you are associated with space research? Oh my gosh. Okay, so yeah, I'm so excited. I'm so excited for people who are at school and going into these decision spaces of like, what is it that I want to do and what problems do I want to solve, or any, that's where my my very enthusiastic brain goes. I would say that exciting news, but your job probably doesn't exist yet. And I'm sure kids get told this all the time of like, your job probably doesn't exist yet. And I know for me personally, that's actually been a hallmark of my career. My next job never exists until I'm either in it or it's like, oh yeah, that's the thing I've been doing. Okay. And then it makes sense when I look. It gets created. Absolutely. And I think the real message here is not what is your job going to be, because genuinely, your job probably doesn't exist already at this stage, or it will look very different to what it does today. What I would say is, what skills or how are you building your passport, right? How are you building your passport to help you navigate a future that you may or may not know? So I see that STEM skills is about filling that passport up, and they are the things that will help you navigate the opportunities.
Can you explain what you mean by STEM skills?
STEM skills. So we think about science, technology, engineering, and maths. And so when we think about those things, I think a lot of people think straight to like the coding or the soldering or the equations or the, how I can build a drone or, investigate science. And all of those things are super critical for sure. But it's actually the mix of them coming together. And I think this is the power of STEM. Or STEAM. I don't want to like start this discussion necessarily on here, but I just think intrinsically it's about the way in which they come together, and they're a suite of tools and techniques that help you uncover the closest thing to reality that we know, and also how you can test and iterate something to work or to do good things. So that's what I mean by like sort of the technology side marrying with the science side, and we see that in science, technology, engineering, and maths. The stuff that is overlaid with that's the glue that I think brings those skills together, are the things that are inherent in those STEM fields. And to be honest, they're things like creativity, it's critical thinking, it's problem solving, it's the way in which you can collaborate and work in teams. That like, there is no single source of all knowledge or single project. Like, you have to collaborate across so many different ways, learning to communicate, working with yourself and working with others. That's what I mean when I say STEM skills. It's not just the hard coding side of things. It's actually how that suite of things comes together. And I am so excited because there's so many cool things that we are seeing that are helping us reduce the suck in the world, so solving problems, but are also providing ways to like make our world more awesome. And I think we need STEM skills for both of those things. And with space, I think there's something incredibly exciting and incredibly inspiring about solving problems at the very edges of our knowledge and the process of discovery and exploration and what that means to be human, to explore. And then from that, how do we know what questions we should be asking? How do we know what technologies we need to help that solution and build things and test things? And how can we understand ourselves as we explore the world around us? And that's not just about space. I just think space is one of just the most powerful ways that we can give that spark, that inspiration to take on those STEM skills. And one of the things that I'm really excited about with our school program with BinRx is hopefully giving individuals, young people, the opportunity to be inspired by space, to be motivated by space, to be better prepared for the challenges of STEM through their schooling, through whether that's high school or university. So we can build these young guns who are motivated and prepared to take on those challenges.
Well, Renae, thank you. Funny you mentioned that. We got a couple of young guns who've actually prepared a few questions for you. I know. Was that a
It was a good segue, but I had another segue that I was going to go to.
Oh,
That's
that's why you were frowning at me.
Yeah.
Not because I'd achieved a good segue.
This is good. I'm just getting. Yep.
Speaking of young guns, so really lovely, two lovely boys. One, Alan, who's in year 5. No, I got that completely wrong. Alan, who's in year 11, he is an astrophysics enthusiast, and Rupert, who's in year 5, who's also very interested in all things space. They meet up every now and then, and Alan sort of mentors Rupert a little bit, and they talk about all sorts of stuff, and it's awesome. And they've given us a couple of questions to throw at you. Now, it's good to see that you've prepared, because these look like complicated ones. So Rupert has asked, what happens if 2 neutron stars fall into each other in the heart of a supernova explosion?
This is absolutely gorgeous. And so what you are describing, Rupert, is what we call a quote-unquote perfect explosion. And this was actually documented. It was published in an incredible, this astronomical marvel. It's actually published in Nature, a Nature paper earlier this year. And what you're describing is something called a cosmic car crash. It's like a killer nova. And so it's a perfectly spherical explosion. And so very, very dense objects. So what you've got are neutron stars, super, 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 super dense. And these are the hearts, the remnants of massive, massive stars after a supernova explosion. And so when you've got these incredibly dense stars, these neutron stars, and they're moving at 100 million meters per second, and they ram into each other in space, that's what we mean by a cosmic car crash. These stars merged and then they collapsed in on themselves to form a black hole while throwing out fragments that produce a perfectly spherical fireball of blue and red. And that's what is known as a kilonova. And it's a ball of optical, ultraviolet and infrared light. And it was observed by astrophysicists at the University of Copenhagen. It was published in the journal Nature, and looking at this incredible, it was an in-depth study of this 2017 celestial event, and it was the first one observed using the ripples of space-time. Thanks you, gravitational waves.
Well, Rupert, awesome question, mate, because that is pretty cool. Sounds like he's keeping up with recent developments in what's going on out there.
I'd love to see someone try and do an artistic interpretation of what people think that looks like and how that would make them feel. It's just remarkable, isn't it? How our brains try and make sense of something like that.
Some AI-generated artwork of that, maybe.
ChatGPT onto it.
Okay, next question is from Alan, and in this one he says, Dear Miss Sayers, the current direction of physics continues to look for a unifying theory combining quantum mechanics and general relativity. What would be the implications should a one-for-all theory of our universe be found?
Oh my gosh. Do you know what?
It's like the dream of physicists, isn't
really
it? To find.
And Alan, this was my frustration studying physics at uni. I felt like I was standing, I would go into all these rooms, but I never understood what house I was in. And every unit, it was, we were over here making sense of we're learning about quantum, and it was just like, okay, this is crazy, this is wild. And then I would try and open the door and work out, okay, where am I in this house? And it was like, oh, no, you're in a completely different building. And then you'd head on over to Einstein's house, and then you'd sort of close the door and open different parts. And so this is the frustration, I think, that the what he's talking about, the grand unified theory, and the desire is for us, for humanity, to be able to further explain this phenomena that we just don't understand yet. Things like dark matter and supersymmetric partner particles and antimatter asymmetry and magnetic monopoles, and some really fascinating, really difficult things that sit on the fringes of, I guess, those theories. And so what it would mean is that we would have a single framework unified to help us understand, I guess, that continuity of physics from the very, very big, where you have gravity absolutely dominating, to the very, very small, where we just have to uncover that with some of the most incredible mathematics and things like quantum mechanics. And so I think this idea is so elusive and so popular with respect to, wouldn't that be mathematically so compelling? But we are yet to have any direct evidence that this is actually relevant to reality. So this may be a very human thing, Ellen, for us wanting to create some kind of unified theory that makes sense to our beautiful brains in this world, but maybe there's something else that we just cannot fathom and cannot comprehend with our hardware and software that we have as humans. But I tell you what, it infuriated me as someone that likes stories and narrative and makes sense of things as they are relative to each other. I found this so difficult. Personally, Alan, when I was at uni studying these things.
Because you wanted a neat place to hang all of these ideas, I guess, or a neat framework to connect them all.
I mean, it wasn't necessarily neat. I do like things to be quite colourful and sometimes messy. I think there's some beautiful expression with that. But it was...
Well, you wanted to know the answer why, right?
I did. I was the annoying kid with why. And I was like, but why is it that we have these really neat theories that fit within these
Their own
bounds?
paradigm.
Right. And then why can't we interface them? Isn't this just a continuity, right? But it's just there's something about it that remains so elusive to that. I think it's a very human thing that we want to be able to. It makes sense that it should make sense, and yet it doesn't.
Awesome. That's awesome, Renae. Thank you so much for answering those student questions. They'll be stoked.
It's incredible.
They will be very happy.
Reach
with
out,
that.
Rupert and Ellen. I'd love to keep talking. I'd love to introduce you actually to some people who can help propagate these fascinating conversations onwards.
Awesome. Steve, before I hit Renae with some of these quickfire questions at the end,
Yep. Look, I feel that we just started, but we're already an hour in. I did want to just ask. Just like a boy-girl question, because you were talking about STEM skills, and you've obviously got a bit of a passion for promoting STEM with girls as well as everyone. But boys tend to be, and I teach STEM, and I know what you're talking about with all those non-technical skills, problem solving and communication. But boys aren't as interested in doing that. They just want to do the technical and don't really see that. I'm generalizing, but they don't see much of the value in the non-technical skill acquisition. And I wonder how is that different with girls, because I imagine it's probably the other way around.
And you've got 2 daughters, by the way.
I do. Yes. Yeah. And so it definitely, from a generalized perspective, I think that if we write the challenges as literally like our program, when we were doing a call for people that were interested to join, we were very deliberate in our language. And it wasn't like, do you know how to code? Do you know how to solder? Are you interested in microelectronics? It was like,
do you like solving problems? Are you creative?
Exactly. Exactly.
Can you communicate? Can you work in a group?
That's it. That's absolutely it. And so looking at, are you interested in those things? And if you can cultivate that environment where people can see themselves in it rather than see the things that they can't do yet. And I think there's a really interesting framework around that to be discussed with respect to how young men and women
give an example. We'll be working in groups, and there'll be one group that's maybe solved the problem, and then the rest of the groups haven't. And I'll say to the other groups, why don't you go and ask them how they did it?
Yeah.
And that doesn't really come into their head. They'll be sitting right next to someone who knows how to do it, but they don't really communicate on that kind of level.
Why
to
do
solve
you
the
think
problem.
that?
Don't know.
I think sometimes that's because they are committed to trying to solve it themselves, even though they've hit a brick wall.
Well,
and they don't want to.
Yeah, and they're committed to the technical instead of the non-technical.
Interesting. I guess
it's a valid way of solving a problem.
Oh, absolutely. I actually think that the real power is that, like, how do I put this? There's research that say, well, the evidence shows that if you've got, for example, women on the board, women in senior executive positions, women at the decision-making table, businesses do better. So it's not just a HR thing of like, we need to have more girls involved with stuff. It's like, oh, you want your edge? You want to innovate better? You want to have diversity of thought at the table? You want to be able to perform better? That's what diversity actually gives you. And we're only really understanding what that means as we're still, I think, as a society, as systems and as ourselves, if we think of the concentric circles that we exist in, really understanding how gender plays a role in a lot of those outcomes. I mean, we've known, but I think understanding how to deal with the sense of self, the sense of system, and the sense of society around that. So it's really interesting. So maybe that's the other thing of how do we facilitate learning where you're exposed to a diversity of problem-solving techniques and developing that sense of resilience around ways of looking at problems and being able to flip it and be able to see what you have around you and overcome those things. I think that's... I don't know if this is answering the question, Steve.
No, it wasn't necessarily a question.
It's my observation.
I was just kind of interested, and I'm observing as well.
And then look, we're still in our pilot phase of BinRx, and we've got lots of different schools, and there's diversity in those teams, and the teachers have done an amazing job. These champions have done an amazing job at, picking out students who, have that intrinsic interest as well as that desire
so when
to
you
connect
are
with
looking
others.
at those students, would it be more of the ones that have the non-technical skills as opposed to the technical skills, or is it a combination of
It's not necessarily. It's
both?
I think it's a combination as well. And one of the most powerful roles that you can play in the space program, for example, is having really good project managers. Like, there's so many different skills that we need. And I guess this goes to maybe another one of the questions that we touched on about the different jobs. What is your job going to be? And things like that. You can have a job in STEM that may not necessarily be the hard skills of STEM. I've had a career in STEM, and yes, I have studied astrophysics and really loved maths, even though I really had to try harder. It did not come naturally to me. I'm much more of a hand waver than seeing the world in numbers, but and relationships, much more about relationships. So the language of maths was very challenging for me. And I've had a career in STEM, but my job has not been the products of STEM. And I think that's a really powerful thing of you can have an appreciation for and an understanding of the power of those tools of inquiry and these techniques that we can poke and prod and do things and achieve things together without necessarily having to be like, okay, I'm going to use these hard skills forever in my job and in my career. So that's, I think, a powerful thing of hopefully putting space in the hands of WA is that we're meeting our community where they're at with respect to, we don't have space in our blood and our DNA, like, for example, the United States has with, for example, NASA. So we have to build a lot of that. In the US, people don't necessarily ask in the same way in Australia, why do we go and explore space? Or people don't necessarily question why we're trying to excite kids with space to do, more STEM. Like, it's just that given of that can provide that catalyst, that uplift that people can see themselves in. And if we can create today the most diverse as possible when it comes to diversity of thought and problem solving, to getting to that place where we're doing great things, as well as people being able to see themselves in our program and therefore it being their program. I think that's the thing that will change the tone to how they will then mentor back down. And so I'm really excited about our pipeline that we've built with the primary school, with the high school program leading into the undergrad program and the internship and there's masters and PhD opportunities in a graduate program, and the whole way through there's like opportunities to go back and mentor. So just like Alan is mentoring Rupert, and as Rupert gets older, I'm sure he will mentor someone else. And so that's a really beautiful propagating system of, as you're learning, you're able to kind of instill back, but you're learning both ways as a value. We learn from the kids today about where they're at and how they learn, as well as, mentors that have been able to achieve things in a different learning environment. So I think it's a two-way thing. I know I learn something every time we see our students engage, and I learn so much from teachers as well, because, the challenges and the beautiful pleasure, privilege that you have, and it's incredible what everyone does. But I think it's that two-way thing as well.
It's a privilege every day, isn't it, Sam, to be a teacher?
It is. It absolutely is. Yeah, well, my
certainly
colleague
would not be boring.
No, and my colleague Akram actually hit the nail on the head, I reckon, when he said
it's honest work.
You don't
got a good purpose.
You don't wake up.
Course.
You don't wake up worrying whether what you're doing is meaningful. I mean, that box is ticked.
Yes.
So yeah, loving it.
Absolutely.
All right, let's do the quick fire. Otherwise, our SD cards are going to run out.
They're going to run out.
Oh, yes.
I really feel for you on the editing side of this. I just want to say.
It's great, Renae. This is bad. We're hardly going to edit anything, aren't we?
Oh, I really hope you edit. I really hope you edit.
Okay. So, first question. Deserted Planet, favourite album?
Oh, wow. I actually will take my liked songs from my Spotify playlist because I don't have a single album, unless the most played thing is Max Richter Sleep, because that's what I listen to every night, me and my daughter. So yes, if I had to listen to something that I like novelty. So my liked songs, I've got all sorts of things in there from actually, yeah.
I can't force you to pick an album.
I can't pick an album. No, I can't pick an album.
Okay.
What a cop-out.
Now, this isn't on this list, but I'm still going to hit you with it. Yeah. If you could write a book, what would it be about?
Oh, it has to be on curiosity. I would just have to find a more novel way of shedding light on something like that and make it... I would want to make people feel joy and feel empowered and feel excited. And so that is what I would like people to feel reading a book about curiosity.
Awesome.
I'd like to make them laugh.
Awesome. Okay. What has been the most beneficial habit that you've formed in the last 5 years?
Getting up early and having that sacred space in the morning, for sure. I mean, my daughter's 4.5, so there's also that is in the particular time zone thing, but for sure that early morning habit, just to carve out a bit of space
for yourself. Yeah.
Yes, For sure.
Yep.
Doing the
I hear
morning
you
pages.
as a parent.
Doing the morning pages.
Maybe that can be the
and
name of your book, Carving Out Space.
Carving out space. Well, I've got the take up space, you know, the sort of saying of like take up space and just, you know, sense of self and self-respect and self-esteem. But it's actually like take up space as in,
Yeah,
let's
get
do
a job
this.
in.
Take up space, get it in.
Be
Yeah,
an
so
astrophysicist.
exactly.
Not you're taking up space.
No,
Sort of
but in a
just
good
like-
way, because you want to take up space, as particularly for women and girls, take up space, and
Love it.
and also take up space. We need you. We need everyone.
All right, last question. Is there anything? Sorry, Steve. I've got.
I'm just freaking out because if
I've got the.
The cameras are going.
I've got
We
the
may
monopoly
lose all-
on
we
this.
may lose
on
all
these
the
last
footage.
Questions. No, that's not true.
it might be. Seriously.
Okay, right. Maybe we should wrap it up. Renae, thank you so much for joining us here.
Do it. Wrap it
Can
up.
we do that? Can we do that without,
Sorry,
without
the
the
giggles.
absolute laughter?
Sorry.
Come on, Renae. This is serious business.
It's been a great time. What have we done again? No, this is wonderful.
Thank you. Sorry. Renae Sayers, thank you very much for joining us at the Range Project here at Scotch College. It's really exciting what you're doing with the Space Centre at Curtin, and all the best with it.
Thank you so much, and I've had a great time. I really hope we see more of your students taking up space.
I'm sure you will. Thanks, Renae.
Thank you so much.
See ya.